Hello and welcome back to ARTS. In today's video, we're going to be going over launch angle decomposition and the two parts of projectile motion. So before we went over both vertical and horizontal motion, right? Now we're going to couple both of those and then we're going to split them. So if you launch an object at an angle, you have two vectors. You have the vector Vy, which goes like this, right? Vy, or it goes up, straight up. And you have the vector vx that goes this way. This time we'll figure out how to use those. We already went over horizontal and vertical motion, but we're just going to incorporate that into projectiles with angles. And we're going to see how things can be a bit different, but in many ways similar. Okay, so this you should already know, right? vxi. If you have velocity initial, right, suppose my projectile was going like this and my velocity initial was this. Velocity x initial would be velocity initial times the cosine of that angle. Velocity y initial would be velocity initial times the sine of that angle. We already went over this in basic vector math, right? This is just revision. So for example, if we had a projectile that was launched at 35 meters per second at 50 degrees above the horizontal. What does it tell you if it was launched at 35 meters per second? Well, that's the first velocity, or in other words, velocity initial. Okay, so I know velocity initial is 35 meters per second. And I want to decompose this into velocity initial y, velocity initial x. So I could draw a graph, or a projectile graph, right? Just shows you the direction of the projectile. And then I can do my y vector in red, Vyi, and my other vector, my x vector in pink, Vxi. So we know that this angle is what, 50 degrees. Right? 50 degrees above the horizontal. So pretty straightforward question here. Velocity y initial would be velocity initial, which is 35 meters per second, times sine of 50. Velocity x initial, same thing, but cosine of 60. 50 degrees. Yep. And that's how you decompose them. So your velocity x would be this one, and your velocity y would be this one. Okay? And then, of course, you can multiply these out, but I'm just going to leave it like this for the sake of simplification and the sake that you can see what's happening here. Where am I getting these different numbers for Vy and Vx from? This doesn't only need to apply to V initial, right? If you had a vector over here, you could decompose that into Vx and Vy as well. I mean, over here at the peak, you don't have any y velocity, right? So this would be only x, but otherwise you would have y velocities. So as always, more comprehensive problems on artslearning.com. Right now, let's just go over some basic ones. So first, I like you to have a try, right? Pause the video and tackle these on. After that, I'll go through them. Okay, I'm assuming you gave it a try. A projectile launches at 40 meters per second, 25 degrees above the horizontal. Find Vxi and Vyi. Vx initial and Vy initial. If you draw a graph for yourself, which you always want to do, and I do that. 25 degrees is our angle. So theta here is 25 degrees. Pretty straightforward. It says above horizontal, so it goes like that. The velocity initial is 40 meters per second. Velocity x initial would be velocity initial times cosine of theta, or in other words, 40 meters per second times cosine of 25 degrees. Always remember the degrees. That's one of the ways you can get tricked here. So you do that, what do you get? 36.25 meter per second is velocity x initial. Same thing for velocity y initial. 40 meter per second times cosine of 25 degrees, which is equal to, sine, right? Because velocity y initial is the sine. So that's one of the common mistakes you made, right? Which I almost made myself. Always want to make sure you catch yourself. Velocity y is sine, velocity x is cosine. And I'm getting 16.90 meter per second in the velocity y initial. Okay, pretty straightforward. What about another question where you have to work backward? If you're given the velocity x initial already as 12 meter per second, and you're given the velocity y initial already at 16 meter per second, how would you find the original speed vi and the angle theta? First, you would draw a graph. Always with kinematics, you want to draw graphs, right? These are more basic problems that don't account for, the more complex ones or more complex realistic situations, but those also would need graphs. So I know my projectile has velocity x initial of 12 meter per second, velocity y initial of 16 meter per second. So if I put this vector over here, right, which is called vector transposition or moving vectors around to add them, right, then my velocity initial would look like this. So if I put this vector over here, you can see how it forms a right triangle, right? And velocity x initial squared plus velocity y initial squared is equal to velocity initial squared because of the Pythagorean theorem. So you do 12 meter per second squared plus velocity y initial 16 meter per second squared is equal to velocity initial squared, or velocity initial squared, which we don't know yet. We get 144 meters squared per second squared plus 16 squared meters squared per second squared, which is 256, is equal to velocity initial squared. Okay, so my pen wasn't working there for a sec. So you add both of these, 144 plus 256, you end up with 400 meters squared per second squared is equal to velocity initial squared. You take the square root of this, and only the positive square root, because velocity initial is going to be in which direction? Since it's going upwards, it's going to be in positive direction, right? The negative would be over here, which is a replacement for this vector. Both these vectors will have the same magnitude. Fun fact, right? At the distance from height, this vector at the distance s will have the same magnitude as this vector from the distance s. But that's just something you can keep in mind. Square root of 400 meters squared per second squared gives us 20 meter per second as our magnitude. Okay? Now let's look at angle measured from verticals. And this can be a bit tricky, so make sure you read the question properly, okay? A launch is 50 meters per second at 30 degrees from the vertical. Find vxi and vyi. which trig function for which leg. So usually we draw the graph and then we go, okay, angle here is 30 degrees. But what is it saying? Is it saying from the horizontal or from the vertical? From the vertical, right? So that means this is what our graph looks like. 30 degrees here. So our actual angle for our actual graph would be 60 degrees. So quick trick that you can get tripped up by, which you want to make sure you know, right? To keep yourself safe. v:'s initial would just be the magnitude of this vector. So the initial vector would probably, I can do in red, has the magnitude 50 meters per second. Okay, so velocity ℔ initial is going to be 50 meters per second times cosine of 60 degrees. And I went over why it's 60, right? 30 is from the vertical, so 60 would be from the horizontal, which gives me, well, cosine of 60 is 1/2, so this is 25 meters per second. Velocity y initial is 50 times sine of 60 degrees, which is √3/2, so this gives me 25 √3 meters per second. Now, what I meant by which trig function for which leg is this could be solved a different way. Instead of doing cosine, so for this vector, instead of doing for 50, you can do cosine to find the right leg, right, this leg. What you can do is, you can say, I want the sine of this angle for the cosine. How do you do that? Well, if you do the sine of the vertical angle, which is 50 sine of 30, and you say that's equal to v:s, well, it's the same thing, because sine of 30 is equal to cosine of 60, right? So you could use the sine function if you were looking at the 30-degree angle instead of the 60 degrees. But then you'd have to swap around a lot of stuff, and it gets messy, right? That's why I prefer to keep it just the regular angle. Otherwise, yeah, so this wasn't that complicated, just simple decomposition to make sure you're good with breaking down vectors, okay? And feel free to see me in the next video where we'll be covering the big three, so something different from the big five: time of flight, range, maximum height, and we'll be going over each one of those, okay? So feel free to give me a like and subscribe if you believe I helped you. And check out my artslearning.com, my website, for more content like this. Thank you for listening.